This is my intermediate algebra course. Today we're going to continue to learn transformations and the library of relations. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In the previous class, we reviewed transformations at the left, and we introduced the idea of relations at the right. You can review this if you'd like. We also introduced the library of relations at the left, and we covered linear, quadratic, square root, cubic, and absolute value relations. Today we're going to cover three more relations: the reciprocal, exponential, and logarithmic. And as I mentioned in the previous class, we're not going to cover the bottom right relation. This relation is typically included in these lists just as a filler, but it's not really covered in the math curriculum, so it's not going to be a good use of your time to go over that in detail. We may study that at the end of the course if we have time. Now, I want you to understand that the relations we're going to learn today are a little more difficult to analyze and graph than the relations we covered in the previous class. So it's especially important that you pay attention and follow directions. If you don't follow the procedures that we're going to learn today to graph these, and they're going to be very difficult to work with. There's two reasons that these relations are a little bit more difficult to analyze. One reason is that the graphs of these relations have a new feature that the graphs of the relations in the previous class did not have, and that is something called asymptotes. Now, what is an asymptote and how do you spell that? A-S-Y-M-P-T-O-T-E. Well, that's a very strange word. An asymptote is an invisible line that a graph approaches. And it usually never crosses the line. It just gets closer and closer and closer and closer. And in this case, the farther you go to the right, the closer the graph gets. You can make that red graph get as close as you want. You just have to go farther to the right. Because our graphs approach these invisible lines, we give the lines a special name. We call them asymptotes. And you can have vertical asymptotes also. And sometimes your graph will approach going up from the right and down from the left. Or you may have a graph that we'll study in future courses where it approaches going up from both sides and so on and so forth. It's important to understand that the asymptote line is not part of your graph. It's just something that we use to help us graph the relation. The other reason that these relations are a little more difficult to study is that in the case of the exponential and logarithmic relations, the bases can change. You may have different bases, but as long as the relations are in this form, they're all considered to be exponential. And if they're in this form, they're all considered to be logarithmic. And because the bases can change, that means the shape of these graphs are going to change slightly, and that makes things a little more difficult. That's not the case with reciprocal relations. Now, the asymptotes that we're going to study today on our graphs, they're all vertical or horizontal asymptotes. You can actually have asymptotes that are not vertical or horizontal, and your graph may approach like that, but we're not going to study those today. So we're going to be asked to write the equations of the asymptotes. So we need to review writing equations of vertical and horizontal lines. Now notice we have a vertical line here. All the points on that line have the same x value. The y values can be anything because your points can be as high on that line or as low on that line as you want, but the x values have to be 1. So we write the equation of that line as x is equal to 1. That's the justification for writing the equation that way. That's the equation of this vertical line. Now over here we have a horizontal line, and all the points on that line, they all have the same y value, -2. The x values can be anything because your points can be as far to the left or to the right as you want, but the y values all have to be -2. to be on that line. So we write the equation of that line as y is equal to -2. So we covered this in my beginning algebra course and my geometry course. Go ahead and try example 3, and when you come back, we'll do it together. All right, we're back. If you said y is equal to 1, that's the equation of that line. Good job. Try example 4, and when you come back, we'll do it together. All right, we're back. If you said the equation of that line is x is equal to 0, good job, because all the points on that line have x values of 0. Now, the whole point of this class is to graph relations by using the basic parent relations and their graphs. So we're going to take these parent graphs and we're going to move them around. We're going to translate them, reflect them, and dilate, and so on and so forth. So the first transformation that we're going to do today is translation, which is moving up, down, or left or right. Remember, when you add a number to y or subtract a number from y in an equation, you move the corresponding graph up or down. If you add a number to x or subtract a number from x in an equation, you move the corresponding graph to the left or to the right. So let's get into practice problems here. It says, write the parent relation and the parent equation of each relation below and use this information to graph the modified equation. Draw the asymptotes on the graph as dotted lines and write their equations. So we're going to graph this relation here. But it's not practical to use a table and just choose random x values, because that would be very tedious. It would be very difficult to have to plug in an x value and solve for y. It would take forever, and it wouldn't give us a general idea of what the graph looks like. So what we're going to do is we're going to find the parent relation and the parent graph and just move that graph to the right or to the left or up or down. Notice we have a variable in the denominator of a fraction. So this relation is going to be the reciprocal relation, because notice here we have a variable in the denominator of the fraction. So we're going to use the reciprocal parent relation. Now, I forgot to mention, go ahead and take a screenshot or a picture of these relations here with your phone. You're going to need these relations right in front of you, this library, as you go through this class. Please take a picture right now, because you're going to need those right in front of you. So the parent relation that we're going to use is the reciprocal relation, and the parent equation is y is equal to 1 over x. We saw that equation down there. So let's go down and look at the reciprocal relation. Notice we have these 6 purple points. Those points are going to be in the same relative location. If you are translating the graph. So if you move it to down, up, right, left, they're going to be in the same relative location. So you want to memorize where those points are, and you have your table down here. So notice we have 1, 1. If you plug in 1 for x in this equation, you get 1 for y, so that's where we get 1, 1. If you plug in 2 for x, then y is 1/2. That's where we get this point here. And if you plug in 1/2 for x, then you get 2. That's where we get this point. And the same is true for the negative numbers. Now, why is it that you plug in 1/2 and get 2? Well, that's a complex fraction, so you can do the math if you want, but it's really better to just simply memorize where those points are. Now, you should know this math by now, but I know that a lot of students, they forget this stuff, or maybe they didn't learn it properly in the first place. But this is a complex fraction. The easiest way to deal with this is simply multiply both sides by 2, 2 times 1 is 2, and 2 times 1/2 is 1, and you get 2. But a lot of students get kind of confused with that. Whoops, I wrote 2 equal signs. So you can consider this fraction symbol to be a division symbol. And remember, when you're dividing fractions, you just change the multiplication and flip the fraction. When you're multiplying a whole number by a fraction, you take the whole number and write it as over 1, and now we're multiplying fractions. When you multiply fractions, you multiply the numerator straight across, and again, you don't have to do this. You just memorize where those points are. Multiply and you get 2 over 1. Multiply the orange and multiply the green, and then we finally get 2. So you don't want to have to do all that stuff, right? So it's better to just memorize that the point 1/2, 2 is on the graph. But we can use that equation to help us remember what those points are, and obviously we have the table down here. So let me show you. It's easier to really just show you how this process works than to try to explain it. So we're going to start at the origin. This is the origin over here at 0, 0. And we're going to move 2 units to the left because 2 is added to x in our relation. Now remember, it's the exact opposite of what you would think it would be. You would think that you would move to the right 2. That's not correct. You move to the left. Then we're going to move down 3 units because we're adding 3 to y. Again, you would think we'd move up, but we're moving down. It's the exact opposite of what you would think. And then we mark our points. So 2 to the left and 3 down. Then we draw a vertical dotted line through that point, and we draw a horizontal dotted line through that point. These are the asymptotes that I was telling you about. In this relation, you're going to have 2 asymptotes, a vertical and a horizontal. We're going to pretend that this point here is the origin. It's not the origin. This is the origin up here, 0, 0. But we're going to pretend that this is the origin, and we're going to use those 6 points. If you look at your table, you see those points. We have 1, 1, so that means go out 1 and up 1. 2, 1/2, go out 2 and up 1/2. These are all points in your table. And again, we're assuming that this is the origin. It's not the origin, but we're assuming that it is. And we just draw those 6 points, and you get the idea by now. We're then going to connect the dots, understanding that our graph, as it goes up, it gets closer and closer to that dotted line. It never touches. And as it goes to the right, it gets closer and closer to that dotted line. And as it goes down, it gets closer and closer to the dotted line. And as it goes to the left, it gets closer and closer. And that is it. That is the graph. So as you can see, it's not that difficult to graph the relation, but we have to use these dotted lines to help us. And a lot of students really don't like using asymptotes, but when it comes to this class, you better get used to these asymptotes quickly, because we cannot graph the relations that we're going to graph today without using asymptotes. We need these. It's also important to understand that the asymptotes are not part of our graph. They just help us to graph. Now you might wonder, well, do we have to draw the asymptotes? And the answer is absolutely yes. In the math curriculum, you're expected to be able to not only draw the asymptotes, but we're going to write the equations of the asymptote lines. Notice that all the points on this vertical dotted line have x values of -2. So we write the equation as x is equal to -2. And all the y values of the points on this horizontal asymptote are -3. So we write the equation as y is equal to -3. So those are the equations of the asymptotes. So you're going to be expected to write the equations of those asymptotes. Now I want you to understand something. You can use the table to help you in your library of relations. but eventually you're going to be expected to memorize where those points are, the 6 reference points. But if for some reason you forget, you can use this parent equation. And if you pretend that this point here is the origin, then you can actually use this equation plugging in values, and you can find this point 1, 1, and -1, -1, and 2, 1/2, so on and so forth, using this equation. If I plug in 1 for x, I get 1 for y. So I go out 1 and up 1, and so on and so forth. If I plug in 2 for x, then y is 1/2. So I go out 1, 2, and up 1/2. So if you forget the points, you can use that equation. Be aware of that. Now it says here we need to write the asymptote equations. Notice that all of the x values of the points on this vertical asymptote are -2. So the equation of that line is going to be x is equal to -2. And all the y values of the points on this horizontal line are -3. So we write that equation as y is equal to -3. And so that's problem number 1. So let's go on to number 2. We're going to graph this relation up here. And notice that we have, again, a variable in the denominator of a fraction. So looking at your library of relations, this is going to be the reciprocal relation, and the parent equation is 1 over x is equal to y. Now you can write y equals 1 over x. It's the same thing. I just wrote it like this because up here are fractions on the left side. So we start at the origin, and we move 3 units to the left, 1, 2, 3, because we're adding 3 to x up here. And we move 1 unit up because we're subtracting 1 from y. And we mark that point. And so we went 1, 2, 3 to the left and 1 up. Now again, you're subtracting 1 from y, so you go up. It's the exact opposite of what you would think. Then we draw a vertical dotted asymptote through that point and a horizontal dotted asymptote through that point. It's the same procedure every time we do this. Now we're going to pretend that this is the origin. Again, it's not the origin. This is the origin. But we're going to pretend that this is the origin and graph those same points. Now look at your table. It should be right in front of you. 1, 1, 1, 1, 2, 1/2, 1/2, 2. Those are all points in your table. And then we have -1, -1, and so on and so forth. So I think you can see what's going on here. And then we're just going to connect the dots, understanding that as we go up, the graph approaches that dotted line. And as we go to the right, it approaches the dotted line. And as we go to the left and down, it approaches that dotted line. Now again, if you forget what those points are, or if you don't have the table in front of you, then if you're willing to pretend that this is the origin, you can use your parent equation. That's why we wrote the parent equation over here. You can plug in 1 for x, and you go out to the right 1, and then 1 over 1 is 1, so you go up 1, and so on and so forth. So that's how this works. Now, I know what you're thinking. You're thinking, why are you making this so difficult? Well, these graphs are not simple. That's why you have to draw the asymptotes. That's why you have to follow these procedures, and you have to pay attention to what we're doing. Because if you don't pay attention and you try to graph these without these procedures, without using the library of relations, without using the parent equation, without using the asymptote, so on and so forth, then you're just going to be hopelessly lost. So you want to follow this procedure. Now the asymptote equations are going to be x is equal to -3 and y is equal to 1, because all the y values of this of the points on that horizontal line are 1. So y equals 1 is the equation of this horizontal line, and x equals -3 is the equation of this vertical line here. Now again, the dotted line is not part of your graph. The green parts are not part of your graph. Only the red curve is part of your graph. We just use the dotted lines to help us graph. So now that you have the general idea here, we're going to start moving more quickly. So what is the parent relation? Well, obviously it's the reciprocal parent relation. And the equation is y is equal to 1 over x. And we're going to start at the origin. And then we're going to move 3 units to the right because we're subtracting 3 from x. And 4 units down, 1, 2, 3, 4, because we're adding 4 to y. And so we're going to pretend that this point down here is the origin. And we're going to draw a dotted vertical line through that point and a dotted horizontal line through that point. And then we're going to, again, pretending that this is the origin. It's not the origin, but we're pretending, and we're going out 1, up 1, and 2, 1/2, and 1/2, 2, and -1, -1, and -1/2, -2, and -2, -1/2. It's the same 6 points in relation to this center there, and we're just going to connect the dots, understanding that as we get close to those, as we go up, down, left, right, we get closer and closer to the dotted asymptotes. That's why they're called asymptotes, is because our graph just keeps getting closer and closer to those invisible dotted lines. And the equations of the asymptotes, the vertical is going to be x is equal to 3, and the horizontal is y is equal to -4. So this is the equation of this line here, and this is the equation of this line here. So now it's time for you to try. I want you to tell me, what is the parent relation? Look at your library of relations. What is the parent relation? You should know that because we've been using the same relation. If you said reciprocal, good. Again, this is the first relation we've been studying today, the reciprocal relation. And what is the parent equation? If you said y is equal to 1 over x or 1 over x is equal to y, good. It's the same thing. You can flip it around. It doesn't matter how you write it. So now I want you to graph this relation up here using your parent relation and the graph on your library of relations there. Remember, you're going to start at the origin, and then you're going to look up here to figure out where you're going to move that point, and then draw your vertical and dotted lines through that point, and remember your reference points, and so on and so forth. So try number 4, and when you come back, we'll do it together. All right, we're back. So we're going to start at the origin, and we're going to go 2 units to the right and then 1 unit up, because we're subtracting 2 from x, so move 2 units to the right, and we're subtracting 1 from y, so move 1 unit up. We're then going to make dotted lines, vertical and horizontal, through that point, and those are your asymptotes. Then we're going to pretend that this is the origin. It's not the origin. This is the origin over here. But we're going to pretend that that's the origin, and we're going to plot those points in your table. 1, 1 is 1 point. Again, out 1, up 1. And 2, 1/2, 1/2, 2, -1, -1, -1/2, -2, -2, -1/2, so on and so forth. Then we're going to connect the dots. And you've seen this a number of times already, so you know how to do this. And there you go. So if you have that graph, good job. Now we have to write the asymptote equations. If you haven't already done that, go ahead and try. The vertical is going to be x is equal to 2, and the horizontal is going to be y is equal to 1. So if you got those right, excellent. All right, so again, you must graph the asymptote lines. You must graph those dotted lines. Even though they're not part of the graph, you must do that. Now try number 5. When you come back, we'll do it together. All right, we're back. So we're going to use the reciprocal parent relation. And the parent equation is y is equal to 1 over x. We're going to start at the origin and then move 4 units to the left and then 2 units down, because we're adding 4 to x and adding 2 to y. Now we're going to draw the asymptotes, and it's just the same procedure that you saw before. And you might be thinking, I don't know why we need to do this. Well, this is a huge part of the math curriculum. Huge part of the math curriculum. You're going to be expected to know how to graph this, and there's no escaping it in the math curriculum. So draw those reference points, pretending that that intersection of the asymptotes is the origin here. You're going to graph those points, 1, 1, negative 1, negative 1, 2, 1/2, so on and so forth. And there you go. So that's the graph. The equation of the asymptotes, if you haven't already done that, go ahead and write those. X is equal to negative 4, that's 1. And y is equal to negative 2. I'm going to write them down here. Just make sure you write a comma in between them. So if you got those answers, good job. All right. On to number 6. Go ahead and try number 6. And when you come back, we'll do it together. All right, we're back. So obviously this is the reciprocal parent relation, and the parent equation is y is equal to 1 over x. And we're going to start at the origin, and we're going to move 5 units to the right. 1, 2, 3, 4, 5, because we're subtracting x. We're subtracting 5 from x. And then we're going to move 1, 2, 3, 4 units up because we're subtracting 4 from y. Again, it's the exact opposite of what you would think it would be. So we're going to mark that point. And we're going to draw vertical and horizontal dotted lines through that point. And we're going to pretend that this is the origin and graph our reference points: 1, 1, 2, 1/2, 1/2, 2, negative 1, negative 1, negative 1/2, negative 2, negative 2, negative 1/2, and connect the dots as usual. And the arrows just mean that we continue, even though we're the window is ending. The equation of the asymptotes, they're going to be x is equal to 5 and y is equal to 4. So if you got those answers, good job. Okay, so that was graphing relations using the reciprocal parent relation and its graph. So now we're going to move on to a different relation, exponential relations. So again, we're going to use parent relations to help us graph these relations here, the modified versions. So what parent relation do we use? Well, notice that there's a variable in the exponent of this expression here. So that means we're going to use the exponential parent relation. And notice in your library of relations, the parent equation is y is equal to a to the x. But we know what a is in this case. A is the blue 2 there, you see. Again, the base changes, as we mentioned, depending on what kind of exponential relation you're talking about. So the shape of the graph is going to change slightly. Now, if you look at your library, we do have good news, and that is that this one purple point here, that remains the same no matter what. And the reason for that is if you plug in 0 for the x value, remember any number raised to the 0 power is just 1. So that's rule number 6 or 7, I forget. I think it's, I forget the number, but this point here is always going to be the same with this basic exponential equation here. But the other points are going to be different. And notice that the graph approaches the x-axis. So that means we have an asymptote actually on the x-axis. So again, it's easier just to show you rather than to explain. We have a dotted line through here, and then we have the graph that looks something like this, but we're going to move up 4 units and to the left 3 units. So we're going to start at the origin using the same method that we did before, and we're going to move to the left 1, 2, 3, and up 1, 2, 3, 4. And we're going to draw a horizontal asymptote. But we're not going to draw a vertical asymptote because there is no vertical asymptote in this graph. But we're going to draw a temporary y-axis. And we're going to, again, pretend that this point here is the origin. So let me draw that again. So now, pretending that this point is the origin, we're going to draw that point in your library of relations. Remember, that point is always the same. It's always 0, 1. And then we're going to now use this equation, the parent equation, to help us find the other points. Now, in the previous relation, the reciprocal relation, you could just memorize those 6 points. But in this case, it's not possible to memorize the other points because they're going to change based on whatever the base of this parent equation is. So we have to use this equation. So now, again, pretending that this point here is the origin, we're going to use this equation, the parent equation, and plug in values to get points around here to see what our graph is doing. So I'm going to plug in 1 for x, and 2 to the 1 power is 2. So I'm pretending that this is the origin here, and I'm going to go 1 out and then 2 up, because anything raised to the first power is just whatever the number is. Now, if I plug in -2, 2 to the -1 power, remember, you use rule number 8, you bring it down, and anything raised to the first power is just whatever that number is, so we get 1/2. But I want you to understand that as you go to the left, I don't really require you to be really that accurate with your points, as long as you know that as we go to the left, as you can see, we're approaching that dotted line, and that's why we need that dotted asymptote. And why did I draw this solid green line? Well, I just drew that to show that we're pretending that, again, that this is the origin here, but we actually don't need that vertical line. So that is the graph. So in some ways, these graphs are a little easier to draw. And the asymptote equation is y is equal to 4, because all the y values of the points on this line are 4. On to the next problem. This is, again, we're going to use the exponential parent relation. And the parent equation is 3 to the x is equal to y. Now, why is it 3 to the x? Well, because the base is 3, you see. So now we're going to, again, start at the origin, and we're going to move 4 units to the right, 1, 2, 3, 4, and 2 units down. Then we're going to draw a dotted line, a horizontal, and we're going to draw a solid temporary vertical. It's not going to be permanent. We're going to get rid of that, and we're only drawing that vertical because we're showing that we're pretending that this is the origin, and we're going to use our parent equation. So remember, if you look at your library of relations, pretending that this is the origin, 0, 1 is always a point on that graph. Now, to find other points, we need to use this parent equation, assuming that this is the origin. Plug in 1 for x, and 3 to the 1 power is 3. So 1, 1, 2, 3. So that gives us another point. And if we plug in 2 for x, 3 to the 2nd power is 9. So we have 2, 9. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we just barely made it onto the window. And then again, I don't really require you to be that accurate as you go to the left, as long as you understand that the graph approaches that dotted asymptote line. So now, remember that solid line was temporary, so we're going to erase that. And the asymptote equation is y is equal to -2. All right. So on to the next problem. Let's try one more of these before you try one on your own. This is obviously the exponential parent relation. The parent equation is y is equal to 4 to the x, because, again, our base is 4 here, so I know it's going to be 4 now. Notice that the bases are changing, so the shape of the graph changes. Now we're going to look to the origin and move 1 to the right and 3 up. Again, because we're subtracting 1 from x and subtracting 3 from y. Then with the exponential relations, we're always going to draw a horizontal and a temporary vertical through that point. Looking at your library and your table for the exponential relation, if we pretend that this is the origin, 0, 1 is always a point, and then we're going to use our parent equation, plugging in 1 for x, and 4 to the 1 is 4, so out 1 and up 1, 2, 3, 4, and that's about as high as we can go, or else we're going to be outside of our window. So we just connect the dots, understanding that as we go to the left, the graph approaches that dotted line. And of course, we're going to erase our temporary vertical. And the equation of the asymptote line is y is equal to 3. So there you go. As you can see, this is not that difficult, but unless you follow these procedures, it can be very difficult. So go ahead and try number 10. What is the parent relation here? It should be fairly obvious because we've done 3 problems so far. It's the exponential. And what is the parent equation? See if you can think of the parent equation. Looking up here, the parent equation is 3 to the x is equal to y. If you got that, good job. And now, I want you to graph. Remember, start at the origin and use this equation here to figure out where you're going to move. And the asymptote is always going to be horizontal. And you're going to draw a temporary vertical. So try number 10. When you come back, we'll do it together. All right, we're back. So we're going to start at the origin. We're going to move 2 units to the left, 1, 2, and 1 unit down. So that's our, that's the point that we're pretending is the origin. I'm going to draw a temporary vertical and the horizontal asymptote. And remember, on your library of relations, we see that 0, 1 is always a point on the exponential graph, assuming that we're pretending that this is the origin here. So now we're going to use our parent equation, plug in 1 for x. So we go out 1 and up 3, because 3 to the 1 power is 3. And I think if we plug in 2, we're going to go above the window. So just be aware that we're never going to go past the horizontal or the y-axis. So connect the dots, and there we go. So if you got that graph, excellent. That should be more curved there. Kind of got a kink in it. So the equation is y is equal to -1. That's the equation of the asymptote, the dotted line. And remember, we have to erase that temporary vertical. So if you got that right, good job. Go ahead and try number 11. When you come back, we'll do it together. All right, we're back. So obviously this is the exponential parent relation that we need to use. Parent equation is y is equal to 2 to the x. And we're going to start at the origin, move to the right 1 and up 2. Because we're subtracting 1 from x in the equation up there. And we're subtracting 2 from y. And 0, 1 is always a point. We're pretending that this is the origin now, 0, 1. And then use the equation here, plug in 1, we get 2. 1 and up 2. And then plug in 2 for x, and we get 4. So 1, 2, 1, 2, 3, 4. Whoops, I don't know what happened to those points there. Write those again. And that's about it. That's all we can fit on the window. So again, you must be aware that as the graph goes to the left, you approach that dotted line and erase the temporary vertical. The equation of the asymptote, that dotted line, is y is equal to 2. So if you got that one right, good job. So go ahead and try number 12. And when you come back, we'll do it together. All right, we're back. So this is the exponential parent relation that we need to use. And the parent equation is 3 to the x is equal to y. Start at the origin and move 4 units to the left, 1, 2, 3, 4, and 1, 2, 3, 4, 5 up. Draw a horizontal asymptote and a temporary vertical solid line, and pretending that this is the origin now, looking at your library relations, 0, 1 is always a point, and plug in 1 for 3 in your parent equation, and we go up 3, and we can see we're already out of the window. So we're not going to pass this line here in our window. So you can just connect the dots, and we only really needed 1 point there because we're pretty close to being out of the window already. So we can erase the temporary solid vertical, and the asymptote equation is y is equal to 5. And there you go. So if you got that answer, good job. Okay, so now we're going to go on to our next relation, the last relation we're going to learn today. Be aware that we're going to not only translate but reflect and dilate. So the next step is to learn how to translate the logarithmic relation, but we need to review logarithms. In the same way that we plugged in values into our exponential parent equation, we're going to have to plug in values to our logarithmic parent equation. And it's important to understand that we can't just plug in any values to a logarithm. because most values that you plug in are going to be what we call irrational numbers. We studied irrational numbers in the past. An irrational number is a decimal that continues, just keeps going, and it doesn't repeat, and it requires advanced mathematics or a calculator, and we don't want to use a calculator, so we're going to plug in special values. So we need to review this basic property here. If you plug in a number into the log function that is the same as the base, then the logarithm just ends up being 1. So that helps us so that we don't have to use a calculator when we graph the relations. Now, why is that? Well, in order to figure out what a logarithm is, you set it equal to y, and then you convert to an exponential equation. Remember, this number here is always the base. Whatever the logarithm is equal to, that's always the exponent. And then whatever's in the log function, that goes on the other side of the equation. So now we can see why y is going to be 1. Because you can write 2 as 2 to the 1 power. And if the bases are the same, that means that the exponents must be the same. So y is equal to 1. But y is what we were looking for in the first place. Y is the logarithm. So we can say that log base 2 of 2 is equal to 1. And that's something you're going to want to memorize. You're not going to want to continue to go back and do this over and over and over again. So for now on, for this class and for the homework, you're going to memorize that if these two numbers are the same, the value of the logarithm is going to be 1. You don't have to show that math. Example 3, these numbers are the same again, so the value of that logarithm is 1. So you can try a couple examples here, but obviously it doesn't really require much work. Try example 4 and 5, and when you come back, we'll do it together. All right, we're back. Obviously, the answers are 1. It's not really necessary to do practice problems, but because these numbers are the same in the logarithms, the value of the logarithms is just going to be 1. So now, we're going to find the value of this logarithm here, but what I'm going to do is I'm going to change 25 to 5 to the second power. So I change this yellow 25 to 5 to the second power. And the reason that I did that is if we convert this to an exponential, or set it equal to y and convert it to an exponential equation, just as we did up here in yellow, what we'll find is that the value of the logarithm is going to be equal to 2. All right, and that's true in every case. So that's where we come up with this property here. So just be aware that if these two numbers are the same, if you can change this number so that the bases are the same, then whatever's in the exponent, that ends up being the answer. So the answer for that one is going to be, we don't have a lot of room, it's just going to be 2. So let's try example 7. We're going to find the value of this logarithm. And in order to do that, we're going to change this number so that it's a power with a base that's the same as this base in the log function. So we're going to change that to log base 3 of 3 to the third power, because isn't it true that 3 to the third power is 27? So, but again, because these numbers here in green, because those numbers are the same, they're just going to disappear, and the logarithm is going to disappear, and the value of the logarithm itself is going to be equal to whatever that power is, 3. All right. Okay, so on to example 8. We're going to find the value of log base 4 of 16, and I'm going to change 16 so that it's a power with a base that is the same as the base in the log function. And then again, using that same rule, the value is going to be 2. Now again, why is this? You can just convert to an exponential equation, set this equal to y, and you can figure it out. But it's not really necessary to do all that work. Just memorize the formula. So try example 9, and when you come back, we'll do it together. All right, we're back. So we're going to change 81 so that it has a base of 9, because now these bases are the same, and the value is just whatever that exponent is. And there you go. So if you got that one right, good job. So we're going to change 16 so that it has a base of 2. So 16 is 2 to the 4th power. Now these numbers are the same, and the value of the logarithm is just going to be whatever that exponent is. We have another property here. It turns out that if this number is 1, then the value of the logarithm is always 0. Now again, if you want to know why that is, just set the logarithm equal to y. The exponent is y, and whatever's in the log function goes on the other side, and 3 to the what power is equal to 1? Well, obviously it's going to be 0. You can change 1 to 3 to the 0 power, and you see y has to be 0. But again, you don't have to do that. Just memorize that if you have a 1 in the log function, then the value of the logarithm is 0. So here we have 1 again in the log function. The value is 0. So in examples 13 and 14, you can guess what it's going to be. It's going to be 0 again because you have 1 in the log expression. So these are important principles that we have to use, these properties, to help us graph the logarithmic relations. So you have these principles right in front of you, and we're going to use them to help us graph the relations. So obviously this is going to be a logarithmic parent relation that we're going to use because we see a logarithm there. So we're going to use the logarithmic parent relation, and the parent equation is y is equal to log base 3 of x. Now why is it base 3? Well, because we have a base 3 up here. Now we're going to do this the same way we did it before, but let's look to that graph. Look on your parent or your library of relations, and notice that the graph looks something like this. And this point is always going to be 1, 0. So in the exponential, we had a point that was always 0, 1. Now we have a point that's always 1, 0. So that's not going to change. That's a good that's a good feature, and that has to do with this property here. You plug in 1, you always get 0. So we're going to use that information, but first we have to translate our graph. So I'm going to start at the origin, and I'm going to move 1 to the right and 2 up because we're subtracting 1 from x and 2 from y. Then I'm going to draw a vertical asymptote. This time we have a vertical asymptote and a temporary x-axis. There. We're gonna pretend that that's the x-axis, and just like we did before, we're going to pretend that this is the origin. It's not the origin. This is the origin, but we're going to pretend that this is the origin, and we're going to use our parent equation to graph the relation. Now again, pretending that this is the origin, 1, 0 is always a point on that graph. So we can go ahead and plot that point. That came from this principle here. We plug in 1 for x, we get 0. Now, again, we have to be careful what values we plug in here. We want to get some other values. We know the curve looks something like this, but we need some other values. So remember, if you plug in a number for x that is the same as this number, you always get 1. That's the yellow up there. You see that? That's the highlighted region up there. So I'm going to plug in 3 for x because the base is 3. So I'm going to go out 1, 2, 3, and then you always get 1 when you plug in that number that's if it's the same as the base. So now, what number do we plug in next? Well, whatever number we plug in for x, we have to change that number so it has a base of 3 in order to use this highlighted property up here. If we plug in 4 for x, we can't change that to base 3, or 5 or 6 or 7 or 8. The next number that we can change to base 3 would be 9. Okay, because we can change 9 to 3 to the second power. And then you get 2. But the problem is we can't plug in 9 for x because we'll go out of the window. 1, 2, 3, 4, 5, 6, 7, 8, 9 will be out here. So what that means is we can't go above this line. So we just connect the dots, understanding that as we go down, we get closer and closer to that dotted line. That's why it's called an asymptote. And then we're going to erase the temporary horizontal, and that's it. That's how you graph logarithmic relations. And our asymptote is now a vertical line, so it's x is equal to 1. And there you go. So again, you should take a screenshot of these properties. We're going to need those as we go along. So the parent relation is the logarithmic relation. The parent equation is log base 2 of x is equal to y. And we're going to start at the origin and move 2 units to the right. 1, 2, and 1, 2, 3, 4 units down. And then we're going to draw a dotted vertical and a temporary horizontal through that point. Now we're going to pretend that this is the origin. And remember, if we pretend that this is the origin, 1, 0 is always going to be on the graph if you look at your library of relations. Then we're going to plug in 2 for x. Why 2? Well, because we want it to be the same as that base down there. If we plug in 2, those numbers are the same, so we always get 1 for the y value. Now, what is the next number we can plug in that we can change to base 2? Well, obviously we can't plug in 3. Can't change to base 2. But if we plug in 4, we can change 4 so that it's base 2. Don't you agree that 4 is the same thing as 2 to the second power? So what that means is the value of the logarithm is going to be 2. So if we go out 1, 2, 3, 4, we can go up 2, and we have our next point there. And now we're ready to connect the dots because we can't really go out any further. Then we're going to erase the horizontal, and that is the graph. The equation of the vertical is y is equal to, or x is equal to 2. All right. On to number 15. Obviously, the parent relation we're going to use is the logarithmic relation. The parent equation is y is equal to log base 4 of x. Why base 4? Because we have base 4 up here. We're going to start at the origin and move 4 units to the left, and 1, 2, 3 units up. And then we're going to have a vertical dotted line and a temporary horizontal. And if we pretend that this is the origin, this point here is going to be 1, 0 always. And now we're going to plug in 4 for x because we want a number that's the same as the base. And remember, when those numbers are the same, the value of the logarithm is just going to be 1, so we go up 1. And the next number we could plug in that has a base of 4 would be 16, but that's going to be too far out. So we just need to be aware that our graph is not going to go above that line. So we can connect the dots, being aware that as we go down, that curve gets closer and closer to the dotted asymptote. And x is equal to negative 4, that's the equation of the vertical asymptote. And we're going to erase the temporary horizontal. Okay, so now time for you to try. You can take a picture of these, number 13 through 15 if you'd like, and try number 16. What is the parent relation? Obviously that is going to be the logarithmic parent relation. And what is the parent equation? If you said log base 2 of x is equal to y, good job. And remember, you're going to start at the origin, as usual, and use this equation to figure out where you move. And go ahead and try 16. When you come back, we'll do it together. All right, we're back. We're starting at the origin, moving 1 unit to the left, 1 unit down, because we're adding 1 to x up here and adding 1 to y. Then we're going to draw a dotted vertical asymptote and a temporary horizontal. And the reason we drew the temporary horizontal is because we're pretending that this is the origin. And if we pretend that that's the origin, then this point here is 1, 0. That's always the same. And now we're going to plug in 2 for x because that's the same number as the base. So 1, 2, and then if those numbers are the same, then the y value, the logarithmic expression, its value is always 1. So we go over 2 and up 1. Now, remember, we can plug in 4 for x, and then we get 2, because 4 is 2 to the second power, so you can get the same base there. So 4 becomes 2 to the second power. These bases are the same, and then the value is 2. Now, you can plug in another power of 2. You can plug in 8. And the reason I know that is because 8 is the same thing as 2 to the third power. And those numbers are now the same. Again, you want to plug in powers where you can change the base so that we have the same base here. And the whole point of that is so you don't have to use a calculator. So if you go out 8, the value of this logarithm is 3. So 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3. So now we can connect the dots and erase that temporary horizontal, and there you go. So if you got that answer, good job. The asymptote equation is x is equal to -1. If you got that, good job. All right, on to number 17. Go ahead and try 17. When you come back, we'll do it together. Okay, we're back. Obviously, the parent relation we're going to use is the logarithmic relation. And the parent equation is log base 3 of x is equal to y. And we're going to start at the origin and move 3 units to the right. 1, 2, 3. And 2 units down. Now we're going to draw a dotted asymptote and a temporary horizontal so that we can pretend that this is the new origin and use our parent equation there. So remember, 1, 0 is always on the graph, and we're going to choose 3 for x because we want these numbers to be the same. So 1, 2, 3, 1. Up 1 because the value of the logarithm is always going to be 1 if those two numbers are the same, and at that point you can see that that's pretty much all we need because we'll go out of the window if we add any other points. So erase the horizontal, and the equation of the vertical asymptote is x is equal to 3. So if you got that one right, good job. All right, on to number 18. Go ahead and try 18. When you come back, we'll do it together. All right, the parent relation that we're going to use is obviously the logarithmic relation. The parent equation is y is equal to log base 5 of x. Start at the origin, move 6 units to the left, 1, 2, 3, 4, 5, 6, and 1 unit up. Draw the vertical asymptote and the temporary horizontal, so we can pretend that this is the origin here using our parent equation. 1, 0 is always a point, and we're going to need to plug in 5 for x because that's the base. Remember, when those numbers are the same, you just get 1 for the logarithm. So we're going to go 1, 2, 3, 4, 5, and 1 for the logarithm value. The next number you'd have to plug in would be 25, because 25 is 5 to the second power. But we don't have enough room for that, so that means we're not going to go above this line here. We may get close to it, but we're not going to go above, so we can just connect the dots. And there you go. Erase the temporary horizontal. And the equation of the vertical asymptote is x is equal to -6. So if you got that one right, good job. All right, so we translated the reciprocal, exponential, and logarithmic relations, and we learned about asymptotes. Now we're going to reflect. Remember, if you change the y variable in an equation to -y, you reflect the corresponding graph across the x-axis. Okay, so it's the opposite of what you would think. You put a negative in front of the y variable in an equation, you reflect across the x-axis. If you put a negative in front of the x variable in an equation, you reflect across the y-axis. And so we talked about reflection in the previous class. These are the same problems that we did before. So first we have to identify the parent relation, because again, we're going to use the parent relation to graph this here. So notice we have a variable in the exponent. So the parent relation we're going to use is the exponential relation. The parent equation is y is equal to a to the x. That's what you see on your library, right? But obviously a is 3 in this case, so y is equal to 3 to the x. So what is different about these two equations in yellow? What's different is up at the left, y is -y. So we have a negative in front of the y. That means we're going to reflect across the x-axis. So what we're going to do is we're going to graph, or we're going to picture it in our head. You can draw it if you want, or you can picture it. We're going to picture the parent graph. And look at your library of relations. You know 0, 1 is always the same point for exponential relations. Look at that point, that purple point on your graph. Then we can use this parent equation, plug in 1 for x, and you get 3. Plug in 2 for x, and you get 9, but I think we're off our scale at that point. And then you just connect the dots. So that's what the parent graph looks like. Okay, we're going to use that to find this graph up here. Now, again, we're reflecting across the x-axis because you're changing y to -y. So what that means is that you figure out the distance from this point to the x-axis, and you go that exact same distance across the other side of the axis and mark that point. So that's going to be here. Then our distance from the x-axis to this point is 1, so obviously we go 1 across the other direction, across the x-axis, and you can see what the graph is going to look like. We can just connect the dots, and there we have our reflected graph. So that's it. We erase our parent graph, and that's how you reflect. Okay, so remember we're supposed to draw our asymptote line. So this graph has an asymptote line there, so I'm going to draw that dotted line right on the x-axis. Okay, I know it's hard to see the asymptote, but all right, on to the next one. So we see we have a variable in the denominator of a fraction. So this is going to be the reciprocal parent relation. And the equation is going to be y is equal to 1 over x. And if you graph your parent relation, remember those 6 points, 1, 1, 1 half, 2, 2, 1 half, negative 1, negative 1, negative 2, negative 1 half, negative 1 half, negative 2. And we have this basic shape. And notice that the x here is changed to negative x, so we're going to reflect across the y-axis. So we're going to take this point here, figure out the distance to the y-axis, and then we're going to go the same distance across the other way and mark that point. And I'm going to figure out the distance from here to the y-axis, go same distance across, and so on and so forth. And you get the point. Now down here the graph is on the left of the y-axis, so we're going to reflect across, and it's going to move to the right side. And so this is the reflected graph. And you can see that the asymptotes are actually in the x and y axes as they are in the parent graph. So we're going to draw those asymptotes right on the x and y axes, because the problem tells us to draw the asymptotes, and the asymptote equations are going to be x is equal to 0 and y is equal to 0, because all the x values of the points on that vertical line are 0, and all the y values of the points on that horizontal line are 0. Now, it's important to understand, I guess, that if you reflect the parent graph across the x-axis, you'll actually get the same shape. That's a characteristic of this this particular relation, but you can figure that out if you attempt that. All right, for this problem, the parent relation is obviously going to be the logarithmic relation. And the parent equation is y is equal to log base 4 of x. And we're going to be reflecting across the x-axis because there's a negative on the y. So if we graph our parent graph here, just to get a feel for what's happening, remember 1, 0 is always a point on the graph. And if we choose special points, choose 4 for x, because we want these bases, or we want those numbers to be the same, because the base is 4. So plug in 4, then the value of the logarithm is always going to be 1. Remember that. If those numbers are the same, the value of the logarithm is always 1. So 1, 2, 3, 4, and up 1. And if we plug in another power of 4, looks like we're going to go outside of our window. So we just connect the dots, and that is the parent graph. Now that's not our graph that we're looking for. That's just what the parent graph looks like. It's going to give us an idea of what the reflected graph is going to look like. So again, we're reflecting across the x-axis because there's a negative on the y. So we're going to count the distance from this point to the x-axis because we're reflecting across the x-axis. It's 1 unit, obviously, and then we're going to count the same distance across on the other side of the x-axis and then mark that point, and that's the reflected point. Now this point here, notice it's on the x-axis, so it doesn't move anywhere. So that's about all we have to do. We just connect the dots. And notice that the asymptote didn't change locations. The asymptote was on the y-axis, and it's still on the y-axis. So now we just erase the parent graph, and there you go. So we want to draw the asymptote as a dotted line, so we go ahead and draw that on the y-axis. And the equation of the asymptote is x is equal to 0. Okay, so it's time for you to try. Go ahead and attempt number 22, and when you come back, we'll do it together. Okay, we're back. Obviously, the parent relation is the logarithmic relation, and the parent equation is y is equal to log base 2 of x. And we're changing the x to a negative x, so we're going to reflect the parent graph across the y-axis. So first, let's draw the parent graph. 1, 0, if you look at your library of relations, 1, 0 is always a point. And if you plug in 2 so that those numbers are the same, we always get 1. So 1, 2, up 1. Again, when these numbers are the same, the value of the logarithm is always going to be 1. If we plug in 4, that's a power of 2. So 4 is 2 to the second power. If those numbers are the same here, then that means the value of the logarithm is always going to be whatever that exponent is. So I plug in 4, you get 2. 1, 2, 3, 4, 1, 2. And the next power of 2 would be 8, but I think that's going to go outside of our window. So we can connect the dots, and this gives us an idea. Well, this tells us what the parent graph looks like. But now we're going to reflect across the y-axis because x has a negative in front of it, so we're going to reflect across the y-axis. So we're going to count how many units from the y-axis to that point, and then we're going to go that same distance on the other side of the y-axis. So 1, 2, 3, 4, and mark that point. So that's the reflected point. And do the same thing over here, and same thing here, and then we can just connect the dots. And you can see that the asymptote did not change its location. The asymptote is still there, so we're going to draw that asymptote as a dotted line on the y-axis, and the equation is x is equal to 0. So if you got that right, excellent. Go ahead and try number 23, and when you come back, we'll do it together. All right, we're back. So we have a variable in the denominator of a fraction, so the parent relation that we're going to use is the reciprocal relation, and the parent equation is y is equal to 1 over x. And there's a negative in front of the y, so we're going to reflect this across the x-axis. But first, let's graph the parent equation. That'll help us understand what's going on here. So remember, we want to use those 6 reference points. You should have your library in front of you. You see those purple points on your reciprocal relation. 2, 1/2, 1, 1, 1/2, 2. Negative 1/2, negative 2, negative 1, negative 1, negative 2, negative 1/2. And connect the dots. And that is our parent graph. And we want to reflect across the x-axis. So what that means is we figure out the distance from this point to the x-axis and then go that same distance on the other side, across the other side, and write that point. Same thing here, and same thing here. Now we have those reference points. And we can connect the dots. And so we started up here on top of the x-axis and we reflected across the x-axis down here, but on this side of the graph we're starting below the x-axis, so when we reflect up. then we can erase the parent graph. And as you can see, the asymptotes didn't change position. And I want to remind you that reflecting across the x-axis gives you the same graph when it comes to the reciprocal relation. Reflecting across the x-axis gives you the same graph that reflecting across the y-axis would give you, so that's just a special case. You'll notice that this is no different than reflecting across the y-axis for this particular relation. So if you got that one right, good job. The asymptote, well, there's going to be two of them, x equals 0 and y equals 0. Okay, go ahead and try number 24, and when you come back, we'll do it together. All right, we're back. The parent relation that we're going to use is the exponential relation because we have a variable in the exponent. And the parent equation is y is equal to 2 to the x. And so the parent graph, remember 0, 1 is always on the graph, and using this parent equation, if you plug in 1 you get 2, if you plug in 2 you get 4, and we can just connect those dots. Anymore, we're going to go outside the window, so we know that it has to stay on this side of that vertical line, the left side of the vertical line. So we're going to take those points and reflect them across the y-axis because there's a negative on the x. So I'm going to count the distance from this point to the y-axis, and then I'm going to go the same distance across the other side of the y-axis to get my next point, or my reflected point. Same thing over here. Now this point is on the y-axis, so it's not going to change its location. And so that is the reflected graph. And notice that the asymptote didn't change positions. It's still on the x-axis. So the equation of the asymptote is y is equal to 0. And we need to draw that as a dotted line. So if you got that one right, excellent. Good job. Okay, so now we're going to dilate graphs. Remember, if you do something to y, multiply or divide, you're dilating vertically. And if you multiply or divide to x, you're dilating horizontally. And multiplication is compression, and dividing is stretching. Now, I want to remind you, we learned in the previous class that dilations can sometimes be confusing. Sometimes a compression can be interpreted as a stretch, and a stretch can be interpreted as a compression, depending on if you're dilating vertically or horizontally. So it's important not to overthink these dilations. Just learn the general definitions that mathematicians have come up with. Also, remember from the previous class, dilations are not rigid transformations. Rigid transformations just move the graph to the right, left, up or down, or reflect, but they don't change the basic shape of the graph. Dilations actually change the shape of the graph. So you're going to need to rely on the equation that you're given to find points on the graph. So we have the same problems here. We have a variable in the exponent, so obviously this is an exponential parent relation. Parent equation is y is equal to 3 to the x. Again, you should have your library right in front of you. And notice that we're multiplying the y value. So we're doing something to y, so it's going to be a vertical dilation. And when you multiply, remember, multiplication means compression, so it's a vertical compression. So our normal graph, if you look at this parent graph here, again, 0, 1 is always on the curve. You plug in 1, you get 3. Plug in 2, you get 9, and so on and so forth. So our parent graph looks something like this. but we're compressing vertically. So that means we're going to push down on the graph. We're going to push down like so. We're pushing down, and it's going to go down. And so what we can do is we can just plug in values. If you plug in 0 for x, 3 to the 0 power is 1. And then you're left with 2y is equal to 1. Divide both sides by 2, and we have y is equal to 1/2. So if you plug in 0, you get 1/2. So notice again, we're pushing the graph down, so that point is now half of what it was before. And let's try plugging in 1 for x. If you plug in 1 for x, 3 to the 1 power is 3, so we're left with 2y is equal to 3. Divide both sides by 2, and we get 3/2. So plug in 1, you get 3/2. But notice that 3/2 is exactly half of 3. So do you see what's happening here? We're reducing the size of the y values by half. So that's the basic idea here. If you multiply y by 2, you're actually taking all the y values and cutting them in half. Now I know that seems like it's the exact opposite of what it should be, but remember that's how this works sometimes. So now we'll plug in 2 for x. 3 to the 2nd power is 9, and then we have 2y is equal to 9. Divide both sides by 2, and we get y is equal to 4.5. So if you plug in 2, 1, 2, we get 1, 2, 3, 4.5, and that's probably good enough. If we plug in 3, we get 27, and I think that's going to be too big. So we can connect the dots. And as you can see, the asymptote didn't really change. So we can draw that dotted asymptote in the x-axis, and the equation of the asymptote is x is equal to, y is equal to 0. And that's that graph. So the same thing happens over here. These values just get closer to the x-axis. It's a vertical compression. All right, on to the next one. Obviously, the parent relation is going to be the logarithmic parent relation. The parent equation is y is equal to log base 4 of x. And we're dividing x, so it's going to be a horizontal dilation. And when you're dividing, remember, it's a stretch. So it's a horizontal stretch. Whoops. Okay, so notice over here it says we need to choose our values wisely. We don't want to have to use a calculator. So remember our log rules, we want the bases to be the same, because then we get 1 for the logarithm. And we want the value in the logarithm to be 1, because then our logarithm is 0, and so on and so forth. So how do we make the inside part here 1? Well, obviously we just plug in 3 for x. So if you plug in 3 for x, we get 3 over 3 is 1, and log base 4 of 1 is just 0. So if you plug in 3, 1, 2, 3, you get 0. So that point is there. And by the way, the parent graph, plug in, or you got 1, 0, that's a point, and then 4, 4, 1, and so on and so forth. So this is the parent graph, and because it's a horizontal stretch, we're going to be pulling it to the right. So let's see, what else can we plug in here? What can we plug in for x to make this whole number here 4? We'd have to plug in 12. That would be too big. So I think that's about it. That's all we can fit in our graph. So we'll just bring that towards the y-axis. I don't really require you to be more detailed than that. And our asymptote is on the y-axis. So the equation of the asymptote is x is equal to 0. Okay, let's try one more of these before you try one on your own. The parent relation is the reciprocal relation because we have a variable in the denominator of a fraction. The parent equation is y is equal to 1 over x, and we're doing something to y, so it's going to be a vertical dilation. And we're multiplying, so it's a vertical compression. So these are our reference points for our parent graph. And so we're going to plug in numbers here. If you plug in 1 for x, 1 over 1 is 1, and then you get 5y is equal to 1. Divide both sides by 5, and y is equal to 1/5. So our first point is 1/5. So that's here. Now, if you plug in 1/5, you get 1. So you can see what's happening here. Now, again, that's going to be a complex fraction. You plug in 1/5. That becomes 5, using the logic we were talking about before, and then y equals 1. So plug in -1, and you get 1/5. Plug in negative 1/5, and you get -1. So you can see what's happening here. I'm just going to connect the dots. And there you go, that's the graph. We can erase these other points. So as you can see, the graph got pushed down a little bit. It got pushed here, and it got pushed up here. And the asymptotes we can draw is dotted lines on the x and y axes. You see the asymptotes don't change position. I'm going to extend that out a little bit. And the asymptotes are x is equal to 0 and y is equal to 0. So go ahead and try number 28, and when you come back, we'll do it together. All right, we're back. So there's a variable in the exponent, so this is going to be an exponential parent relation. The parent equation is y is equal to 4 to the x. And we're doing something to x, so it's going to be a horizontal dilation. We're dividing, so it's going to be a horizontal stretch. So if we plug in 0 for x, we get 1. If we plug in 5 for x, we get 4 to the 1 power. So 1, 2, 3, 4, 5. 4 to the 1 power is 1, 2, 3, 4. And so you can see what's happening here. There's our curve. And I don't really require you to be much more detailed than that. So the asymptote equation is y is equal to 0. And there you go. If you got that right, good job. Try number 29, and be aware that you have to choose your values wisely. You need to choose an x value that's the same as the base there. So choose 3 for x, because when these two numbers are the same, the value of the logarithm is just going to be 1. Also, remember, you can choose 1 for x, and then the value of the logarithm is going to be 0. That's always true. So go ahead and try number 29, and when you come back, we'll do it together. Okay, we're back. The parent relation that we're going to use is obviously the logarithmic relation. The parent equation is y is equal to log base 3 of x. And we are doing something to y, so it's going to be a vertical dilation. And we're dividing. Remember, whenever you divide, it's a stretch. So a vertical stretch. And so we have to be very careful about what numbers we plug in here. So again, I'm going to plug in 3 for x, because then these two numbers are going to be the same, and the value of the logarithm is going to be 1. So then we have y over 4 is equal to 1. Multiply both sides by 4, and we get y is equal to 4. So if you plug in 3 for x, you get 4 for y. So 1, 2, 3, 1, 2, 3, 4. Now, if you plug in 1 for x, remember the value of the logarithm is going to be 0, and then we get y over 4 is equal to 0, and then we solve for y, and y must be 0, multiplying both sides by 4. So if x is 1, y is 0. So notice that that important point on our parent graph didn't change location. Now we're just going to connect the dots because we can't really go any farther up. And I don't really require you to be much more accurate than that. And our asymptote, notice it didn't change locations. It's right on the y-axis. So the equation of the asymptote is x is equal to 0. So if you got that one right, good job. Go ahead and try number 30, and when you come back, we'll do it together. All right, we're back. So we have a variable in the denominator of a fraction, so it's going to be the reciprocal relation that we're going to use as the parent relation. And the parent equation is going to be y is equal to 1 over x. And we're doing something to x up here, so it's going to be a horizontal dilation. But what type of dilation? Is it going to be compression or stretching? We're multiplying x, so it's going to be a compression. And so if we plug in 1 for x, then we get 1/2. So I'm going to mark that point. And if we plug in negative 1 for x, we get negative 1/2. So I'm going to mark that point. And if we plug in 1/2 for x, then we get 1 over 2 times 1/2. And don't you agree that 2 times 1/2 is 1? So we get 1 over 1, which is 1. So if we plug in 1/2 for x, we get 1. So I'm going to mark that point. And if you plug in negative 1/2, you also get 1, but except negative 1. So we're going to connect those dots. Usually we have 6 reference points, but in this case I'm just going to do 4. That's good enough for this particular graph. And the asymptotes, again, notice that they did not change locations. They're still the same asymptotes, x equals 0 and y equals 0. So if you got that one right, good job. Okay, that was the class today. So now we're going to take screenshots of all the work that we did to help you with your homework or to study for tests. So here's screenshot number 1 and number 2 and number 3 number 4, and number 5, and number 6, and number 7, and number 8. But don't go before you get your homework. So let's take a look at the homework. Okay, so here's the homework assignment. And here's the answers for the homework. So get that homework done completely and correctly and neatly, and keep it in order in your binder. And I'll look forward to seeing you in the next class.